the next two slides that we're going to talk about are theorem 3 and theorem 4. Basically, what we want is this. If I give you a sequence and ask you for its limit, you have to know how to calculate the limit. And calculating the limit of the sequence sometimes can be non-trivial. Theorem 3 and Theorem 4 are just the tools that will help you to calculate the limit of a sequence. So these are the theorems or tools that you need to learn. So let us look at the Theorem 3. These are two very simple methods that allows you to work out the sequence of the limit of a sequence. So say you are given a sequence of 2 raised to the power of 1 over n. And the question asks you what is its limit. The limit of this actually is 1. So we said the sequence of 2 raised to the power 1 over n converges to 1. But how are you going to show that? So this is the example of Theorem 3. The Theorem 3 says this. It says if you have a sequence of real number, so given that sequence an is a sequence of real number, not a sequence of complex number. And then if the limit of a sequence an is L, so this is the first condition. Then the second condition that if you have a function f and the function f is continuous at L, so this is the second condition. And furthermore, you have a third condition, that is the function f is defined for all an. If you have such a function f and an that fulfill condition 1, 2, and 3, then the limit, then you can take the function of an or the sequence of an to be just given by the function of L evaluated at L. So in this sense, you can think of an as a sequence. Then you can imagine that each term an is slotted into the function of f. Then since an runs from 1, 2, 3, 4, 5, so you can imagine that the functions with an argument of an also form another sequence. So there are two sequences involved here. First is the original sequence an, and you know what is the limit of the sequence of an. And you are asked to calculate what is the limit of the sequence of f of an. So the questions of finding the limit of the sequence f of an is simply equals to f equal f evaluated at a. I'll give you the example here. Say you have a sequence of here 2 power. You have a sequence of 2 raised to the power of 1 over n. And you are asked to calculate what is the limit of this sequence when n goes to infinity. So just look at the sequence of 1 over n first. So you can imagine that this 1 over n forms a sequence. Then you can also form another sequence, which is like this. So that would be a sequence of fn, so of f of 1 over n, where 1 over n is a sequence of 1, 1 over 2, 1 over 3, 1 over 4, etc. So the sequence of f over n would be, see the sequence f here is defined as x to the power of, here I've defined my f to be a function which is in the form of 2 raised to the power of x. So if I define my function fx to be 2 to the power of f, define fx to be the function of 2 raised to the power of x, then f of 1 over n in the sequence will be of the form 2 to the power of 1, 2 to the power of 1 over 2, 2 to the power of 1 over 3, 2 to the power of 1 over 4. Okay? So now we ask this question, what is the limit of the sequence of f of 1 over n. According to the theorem we have just discussed here, the theorem 3, the continuous function theorem for sequence, we have to have three conditions. We have to know what is the limit of the sequence an, and we have to have a function f that is continuous at L, and we have to also make sure that the function f is defined for all an. So let me look at my function f here. Here my function of f is 2 power of fx, 2 power of x, and indeed that you can find that the function f of x is defined for all an, where my an is just 1 over n. So you can actually quite sure that the function f is defined for all x equals to 1 over n, where n is integer. For example, f of 2 power 1, f of 2 power half, f of 2 power 1/3, etc. are all defined. That fulfills one of the criteria in the continuous functions theorem for sequence. Then the third requirement is that the function f is continuous at L. So since the fx is function of 2 power x, then we can be sure that the function fx is continuous at all values of x, including x equals to L. What I'm trying to tell you here is that I have tried to argue that this function fx that is defined as 2 power x, it is continuous at L, and it is defined for all an, and at the same time also we know what is the limit of an when n goes to infinity. We know what is L. So given by the questions, the L is a number, and we can actually work out what is the limit of an. So here an is a function of 1 over n. Therefore, we know quite sure that the limit of the sequence an, which is L, is just equals to 0. So we have now know what is the L. Now, according to the theorem 3, the continuous function theorem, we are able to answer the questions. What is the limit of the sequence 2 raised to the power of 1 over n? This is just simply equals to the function f evaluated at L, which is equals to 2 power of 0, which is equals to 1. So that is how we make use of theorem 3 to calculate the limit of the sequence. So that is a brief explanations of how to apply theorem 3 to calculate the limit of an sequence 2 to the power of n. Theorem 4 is also another simple tool that allows you to answer the questions of the limit of a given sequence. So theorem 4 is not complicated. It's actually a much more useful or much more easy to use theorem than theorem 3. In theorem 3, you have to invent your own function fx, and then you look at the function fx evaluated at each term in the sequence. Then you have to make sure that f fulfill condition 2 and 3, and then you also need to know what is the limit of the sequence L. Then putting this together, you'll be able to use theorem 3 to help you to calculate the limit of a sequence. In theorem 4, things are slightly different, but it's actually easy to understand. It says this: if you have a function an that is defined for all the term n equals 1, 2, 3, 4. Now imagine this. Imagine you can find a function f that can somehow map the sequence into f. When I say map, I mean this. I mean you define a function fx such that whenever x is equals to n positive integer n, it is equals to fn, right? So for example, if f an is 1 over n, and if you define fx as 1 over x, then every time when you slot in to x a positive integer n, then this is equal to 1 over positive integer n. So that is what I mean by mapping and sequence into an continuous function. And according and defined to be identical to each term of an each term in the sequence for x larger than n naught, then this theorem applies. Now let me explain a little bit further a point which I have not explained earlier on. Now, given a sequence, you can always come up of a function, and the requirement is that you don't really need the fx to be equal to an for all n. You don't need this to be fulfilled for all n. You only need fn equals to an only for all n that is larger than some number n naught, where n naught is just positive number. So it means that if you imagine you plot the function of an versus n, and then you start with 1, 2, 3, 4, blah, 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 you only need to define a function fx that is mapped to an for any n that is larger than a certain number. As long as there exists such a number of n naught, where all the n that is sitting on the right of n naught fulfill the condition that f of n equals to an, then this theorem would be applied. So the requirement that fn map with the terms in the sequence it is slightly not so rigid. You only need this to be fulfilled for n larger than n naught. So anyway, it says that if you have a sequence of an, and if you can find a function f that map a sequence to an, then the limit of the function fx when x goes to positive infinity, if this limit exists, then it will imply that the limit of the sequence is just equals to the limit of this function. That is what it says in the theorem 4, which is known as I think it doesn't have a name, it's just called a theorem 4. It's just saying that the limit of the sequence could be inferred from the limit of an function. So this is a very, very simple example. You are asked to find what is the limit of the sequence n over n. Okay, so now our questions is this. I'm giving you a sequence where the sequence an is given in terms of ln over n, and n is 1, 2, 3 up to infinity. And I ask you what is the limit of the sequence. So this is a shorthand notation to represent the limit of the sequence an. So according to theorem 4 that we have just explained, you can try to create a continuous function that is expressed as ln x over x. So here it is simply replacing the n by x. When you replace n by x, then you call these functions fx. So here it is understood that whenever x is taking a positive number, then f at n is just ln over n. So that means this fx function maps the sequence term by term for n that is larger than 1. So here n naught play the role of at 1 here play the role of n naught. So according to theorem 4, if you can find the limit of the function fx at infinity, And if this limit can be found to be L, that would infer the limit of the sequence AN is also L. So now the questions of finding the limit of the sequence Ln over n is translated into finding the limit of the function ln x over x. So ln x over x is behaving like an indefinite form, because when x goes to infinity, log of x goes to infinity. X goes to infinity, of course, x is also going to infinity. So this is an indeterminate form. Therefore, we have to apply the L'Hopital rules to calculate the limit of ln x over x. So I'm going to apply the L'Hopital rule once. When I apply the L'Hopital rule once, then I take the differentiations of log of x, which gives me 1 over x. The differentiation of this gives me 1. So when I write down these equations, on the right hand side, I am applying L'Hopital rule. Once I have written L'Hopital rule, then I can obtain the answer to be just 0, because 1 over x is just 0 when x goes to, so 1 over x will tends to 0 when x tends to infinity. Therefore, the L that is obtained for the limit of the function fx is 0. Therefore, it implies that the limit of the sequence ln n over n tends to 0 as well. That is a very, very simple applications of the theorem 4 to this sequence. And we're going to continue to discuss example 9. So we have a sequence like this, where the terms an in the sequence is given by n plus 1 over n minus 1 raised to the power of n, where n is an positive integer that lasts from 1 to infinity. And we want to know what is an limit. So when I write down this one, what I mean is that I'm looking for the limit of the sequence of an. So we are going to use the theorem 5. Now in theorem 5, we have to find a function fx such that fx fulfill the condition that when you replace the x by n, then the values of the function f for any n must be equals to an for n larger than some positive values of n naught. What I'm going to do is I'm to choose a function fx that is appropriate. So in order to choose the function, I just have to refer to an, then just replace n by x. That would be the expression for my function of fx. X plus n, x minus n raised to power of x. Whenever I calculate the values of f at x equals to some positive integer, will be equals to an. The statements that f at n equals to an is true for all n that is larger or equals to 1. So here we have a function that is fulfilling theorem 5. We want to find what is the limit of an when n goes to infinity. This limit could be obtained from the limit of fx. According to theorem 5, the limit of fx when x tends to infinity, if this limit exists, then it infers that the limit of an when n goes to infinity is the same as m. Therefore, calculating the limit of the sequence an now is translated into calculating the limit of fx when x goes to infinity. So now we have to look at the expression of fx, and I'll call the expression of x plus 1, x minus 1 power x, a symbol, I call it y. Okay, so I'm going to find out what is the limit of y when x goes to infinity. So I have mentioned that if you have a function that is raised to any power, taking the log would allow the power of r to be brought down. And what is left is the product of a linear r times the log of x. Right? So in this sense, you are reducing the power of x of r into the product of two terms. The first term is linear in r, the term is linear in log of x. So when you take the log on both sides, then the left hand side becomes x times log of x minus 1, x minus 1. Then the right hand side becomes log of 1. You look at the left hand side. You take the limit of x goes to infinity for the left hand side, which is L times log of x plus 1 over x minus 1. So before you proceed on, you have to be able to analyze the behaviors of this expression. So here x will be going to infinity, and what would this be? This x plus 1 will be going to infinity when x goes to infinity. Likewise, x minus 1 will also be going to infinity. So in the limit where x goes to infinity, the ratio will be approaching a value of 1. This argument will tend to 1 when x tends to infinity. So that would mean that log term will tend towards 0 when x tends to infinity. So this is then a product of x multiplied with 0. Okay. So what you do is that you would take down the log of you take down the x term and put it into the bottom so that it becomes 1 over x. These two equations, these two sides of the equation are exactly the same, except that I'm just taking down the x into the bottom so that it becomes 1 over x. Now with this, then upstairs will behave like and 0, and downstairs it will behave like what? When x goes to infinity, 1 over x will behave like 0, right? So by doing this simple act of replacing x into 1 over x in the denominator, this will behave like an behavior which is 0 over 0, which is an indeterminate form. So I have just proven that this expression is an indeterminate form when x is tending towards infinity. Therefore, I can apply the L'Hopital rule. The L'Hopital rule says that this limit is the same as the limit of x going to infinity dx of ln of x plus 1 over x minus 1 over dx of 1 over x. So that would be kind of a complicated expressions to evaluate. And I'm not going to evaluate this expression. Instead, I'm going to copy this result from the slides. So from here to here, I am just rearranging x to become 1 over x. Then I apply the L'Hopital rule. Then this term will be transformed into this form after the L'Hopital rule. So making some small rearrangement, then this expression will then be expressed as this. In the limit when x goes to infinity, then I obtained a limit of 2. So when I come back to here, it is found that then the limit is just equals to 2. In other words, the limit of the left-hand side when x goes to infinity is just equals to 2. I have just written down these equations. Then I evaluate the limit of this when x goes to infinity using the L'Hopital rule. And I found that the limit of this is equals to 2 in the limit x goes to infinity. Therefore, I can safely say that the limit of y when x goes to infinity is 2. You can then simply take the exponents on both sides. So when you take the exponents on both sides, then what you can conclude is that in the limit when x goes to infinity, the exponents of the log of y is equals to the exponents of 2. When I take the exponents of the log of y, then what I recover is y. Okay, then this is just equals to exponents of 2. The limit when x goes to infinity y go to the values of exponential of 2. So that is how you come to the conclusion that the limit of fx when x goes to infinity is just equals to exponents of 2. That infer that the limit of an will goes to exponents of 2. So that is an example of the applications of the theorem number 4 when it's applied to calculate the limit of this sequence. Okay, so it's not so trivial, but the idea is quite simple. That is, you have to first take the log of the function fx, then take the limit of x goes to infinity, calculate the limit of this function of fx using the L'Hopital rules. Finally, once you have found the limit L, which is e power 2, then we said that the limit of the sequence an is just e power 2. So here, calculating the limit of a sequence is transferred into the problems of calculating the limit of the function of fx.